Hey everybody, we have Alexis with us at the Colonomic Action Team, and he'll be talking more. Hey everybody, we have Alexis with us at the Colonomic Action Team, and he'll be talking more. Hey everybody, we have Alexis with us at the Colonomic Action Team, and he'll be talking more about the living energy farm that he's working on, and he has a great presentation. So those of you who were here last week already know Alexis, and he'll talk about what he's doing and what he's doing to improve the world a little bit, and also about himself. So those of you who don't know, I recommend that you go back and watch the replays that we have on our website. And also we have some winners. So last week there was a prize announced. Wayne announced that there'll be 10 winners who will be upgraded to the pro membership for free. So those of you who are winners, you should have gotten an email from Wayne saying that you're the lucky winner, and now you're upgraded to pro membership. So in about 4 minutes, we'll get started with the second week of Alexis presentation. And so welcome to all, and thanks for joining. So Alex, how are you today?
I'm good. How are you?
All right, we're all good. So Alex is in Virginia, and it's beautiful. I can see behind him the window, and it's beautiful, warm day. So I don't know where you guys are at. Those of you who are joining right now. So please type in where you're from and what is the weather like, and that's how we start most of our webinar. We're going to talk about the weather a little bit, and just say how you are, and we'll get started in about 2 minutes. We'll start the presentation, and we'll go from there. So everybody, please feel free to type in your questions and type in where you're from and what is your situation. I know that there's audience from all over the world. So we have audience from almost all the continents except Antarctica and the polar regions. So rest of the world, we have people from Australia, Europe, Africa, America, Latin America, and all those places. Um, so Mark Harris, he says, Mark is urban homesteader from Southern California, sunny and warm, and so is the weather. Okay. All right. Thank you for that, Mark Harris. So anybody you know, who is new to our platform, please type in where you're at and what is your situation, and we'll get started in about 2 minutes. So I'm going to right now. I'm looking at the audience, and there's a bunch of you who are new, and a bunch of you who are our regulars. So I see Alicia is here. Helen, I don't know if you were here last time. Jan is here. So welcome to all of you. Um, Feel free to type in your questions at any time, and in about 2 minutes, I'll turn it over to Alex, and he'll start his presentation. Um, so if any of you were here last week, type in a 1 and type in a 9 if you weren't here last week. Let me see how many of you are returning audience, and it would be really great if you haven't seen the first one and you go back and watch that. So in about a minute, I'm going to turn over to Alex, and he will begin his presentation. Um, so all right, people, Once again, this is Economic Action Team. Thanks for joining. And I'm going to go over to Alex. Alex, uh, it's all you now. So we'll begin your presentation right now. So take it away.
Okay, very good. Today we're going to talk about, hold on, let me get my computer straightened out here. There we go. We're going to talk about what we call a DC microgrid at Living Energy Farm. Although I'm realizing our use of the word solar is, people think they know what that word means. So I think we're going to change our terminology coming up here shortly. I think we're headed towards a community energy self-sufficiency program. We've realized in talking about solar energy that people think we're talking about the way other people use solar energy, and that's not how we use solar energy. So what we're going to talk about today is what we've been calling a DC microgrid. I'm going to start out by telling you that we use both high voltage and low voltage DC electricity. We get high voltage DC electricity by putting photovoltaic panels in series. I need to warn you that high voltage electricity is more dangerous than high voltage DC electricity that you get off of solar panels is more dangerous than high voltage AC electricity, or at least as dangerous. So this is not something, if you have no clue about how to handle electricity or how to properly put together wiring, you're accepting your own risk. You're doing this at your own risk. You find somebody who's a capable electrician before you pursue any of this high voltage stuff, especially. It can hurt you. It could kill you. I don't know if anybody has been killed by it, but it could certainly could. So the DC microgrid we have at Living Energy Farm is extremely efficient. It is financially efficient. It is very effective. But why would you want to build one? Well, let's look at our options. So the regular AC grid, and AC stands for alternating current. If you are connected, if you're in a normal home with receptacles in the walls and all of that stuff, that's AC current. That's normal electricity. Of course, you have to pay your monthly bill. Energy companies these days are consolidating into massive corporations that are having a negative effect on our democracy. They don't care about you. They don't care about your family. They don't really care about the impact on the environment. There's massive environmental destruction connected to supporting the AC grid. Here in the East Coast, we have mountaintop removal, where they take down entire mountain ranges. They'll blow the top off of a mountain for 6 inches of coal. They throw the top of the mountain in the valley, cover up the river, dig the coal out, and leave a lot of rock and a little bit of grass behind. The nuclear waste we're generating will last into the future longer than humans have existed as a species in the past. Climate change, I'm not going to give you a long lecture on that. You're familiar with that, I imagine. All of that are negative effects of the AC grid. Back in the 70s and 80s, recognizing these negative effects, people started trying to develop off-grid solutions. There's some big problems with the normal off-grid design. They fail easily and often. AC motors have to have a perfect voltage. Inverters, that's how you make DC power from a battery set into AC power. These electronic inverters have to have almost perfect voltage. Those systems, when they weaken, they fail easily, they fail often. People have backup generators. They get frustrated with them, they throw them away. And the big kicker on those normal off-grid systems is you're looking at about $1,000 a year in battery degradation for a full-size system. Even a smaller system. The battery degradation is pretty horrible. A DC microgrid, this is what we have at LEF, operates at very low cost, almost free once built. Our annual battery degradation cost is probably about $25, somewhere around that. Allows a community to achieve a large degree of energy independence. So we're not dependent on big energy corporations. Communities that are supported by independent energy can be the foundation and future of democratic society. People think of, we have a very mentalist approach, and that's because of a lot of upper class people, a lot of professionals who want to make you think they're important. So they always talk about mental things and assume that things material are less important. If you look at it from a broader historical, anthropological standpoint, the foundation of democracy has to be based in the economy, or it will not sustain. There's a lot of anthropological historical theory we could talk about behind that, but that's not the focus of today's presentation. So we'll just say that a democratic society can't be built on a centralized economy or can't sustain itself. Our DC microgrid has a radically reduced environmental footprint. It's not free, but it is radically cheaper and a dramatically lower climate change impact. How not to build a DC microgrid. The big problem with how solar energy is used now is you can't go up to people and they want you to support what they're already doing with some form of renewable energy. You can't do that. It doesn't work. So if you take our DC microgrid and you try to adapt it to large private homes with air conditioners and toasters and blenders and tumble dryers, your approach will be expensive, ineffective, and unsatisfactory. If you look at the last presentation we did, we talked about context, conservation, then renewable energy. You have to restructure how you live, how you use energy to make renewable energy work. Renewable energy works fantastically well at a village level. We can support a middle-class standard of living or a very comfortable standard of living, but it has to be, for it to work really well, it has to be restructured from the beginning. So you can go back and look at that webinar. But the point here is you can't just stick a DC microgrid onto existing AC residential industrial systems. It won't work. Although you can, in fact, put pieces of it on there, but for these systems to work really well, they need to be integrated. So we're going to talk about some basics of electricity. AC electricity is the kind of electricity available in a normal house. It travels as a sine wave, as per the curve on the page there. The voltage is easily adjusted. A long time ago, people realized you could use a transformer. Transformer is just two coils of wire wrapped around each other, basically, and the size of the relative size of the two coils of wire allows a transformer to step up voltage or step down voltage. So you don't need modern electronics. Transformers have been around for a long, long time. High voltage AC, they use transformers to step up AC at the power plant. The big transmission lines you see are 500,000 volts. Some of the biggest ones go up over 800,000 volts. That allows AC power to travel for hundreds and hundreds of miles over wires, and that's the basis of the grid as we know it. This is based on the fact that back in the early 1800s, when we first started using electricity in a widespread fashion, the only source of electricity they had back then were generators. We didn't have photovoltaic panels in 1890. So they built big generators based off of steam engines, connected to steam engines, and built a centralized AC power grid off of that high voltage AC power grid. DC power is fundamentally different. It's represented as a straight line, just constant electrical pressure. Photovoltaic panels are fundamentally different than a steam boiler, but we continue to treat them like a steam boiler because we're locked into old habits. So DC power comes from photovoltaic panels, which I'm just going to call PV, or from batteries. Wind turbines can generate AC or DC. That depends on just how it's built. One big difference, a couple of big differences about AC and DC. DC power does not travel down a wire for hundreds of miles. You can send it a few hundred feet, and that's fine, but you could not build a national level DC electrical grid. It wouldn't work. But I would suggest that we don't need a national level DC electrical grid. What we need is to get rid of the grid and have energy self-sufficient communities. A big advantage of DC equipment is that DC equipment tolerates huge voltage swings. So AC motors, AC inverters, all of this AC equipment that has to have a spot on voltage, DC equipment, for the most part, the voltage and the power supply can float all over the place. Now there are limits. You can only go so far with that. But that said, there's a lot more flexibility with DC equipment than there is with AC equipment. Changing voltage with DC equipment is more complicated. You can't do it with a simple transformer. There's several different ways of changing voltage, and let's talk about those. The 4 different ways you can change DC voltage. And the reasons we want to change DC voltage is because there's a lot of different kinds of motors. There's a lot of different things we can do with DC power, and being able to change the voltage or change how that electricity is being generated gives us tremendous flexibility in how we use it. So there's 4 ways to change DC voltage. You can do panels or batteries, PV panels or batteries in series or in parallel. That changes the voltage. Something called maximum power point tracking is an electronic device that changes voltage. DC to DC converters, also called regulators, can change DC voltage. And switching power supplies. We'll talk about each one of these in turn. So the main solar rack we have at Living Energy Farm is simply 6 PV panels. Most of the PV panels made these days are in the 30 volt range. That means they run about 30 to 35 volts peak voltage. All of these voltages are nominal, by the way. So if you take 6 nominal 30 volt panels, put them in series, and this drawing shows you how to do series. You do You take the plus and minus cables coming off of the panels, you go plus minus, plus minus, plus minus all the way across till you get to the end. You have plus minus, as I hope you can see in the drawing there. If you do that with 6 30-volt panels, you get 180 volts. Actually, on a sunny day, that's probably 230 volts, but that's okay. DC voltage, DC equipment can handle those kind of voltage swings. On a cloudy day, we might have 120, 140 volts. DC motors are fine with that. So what happens when you put things in series, basic electrical theory, volts times amps equals watts. Watts is the actual amount of power you can do. Volts is like the electrical pressure. Amps is like the electrical volume. You can think about it as a water metaphor. Either way, you get the same amount of power. You can either add up the pressure with the same amount of volume, that's series, or with parallel, as you can see in the bottom of the page, you add up the volume and keep the voltage the same, and you still can do the same amount of work. If you're adding up amperage in series, you need a bigger wire. Amperage is what heats up wires. So for instance, at Living Energy Farm, most of our daylight drive equipment is the high voltage system that's in series, but we run some irrigation pumps and whatnot, low voltage, like you can get cheap scooter motors in the 12, 24 volt range. You could put, let's say we've got some like 1/3 horse scooter motors. They're made to run a little battery powered electric scooters. We'll put a couple of panels in parallel for those. So the panel's putting out around 30 volts. That's okay for a 24 volt motor. We get enough amperage to run the motor, but you have to pay attention. You can look it up online, wire sizes. If you're an electrician, you kind of know it in the back of your head in terms of what wire will handle what amperage. But certainly when you start doing things in parallel, you need to think about wire sizes. Another way to change voltage is with what's called maximum power point tracking for battery chargers. These are expensive computerized devices. This is the one we have at LEF. It's called a Midnight Solar. It's a good company. It's a fine little device. This one's about 350 bucks. This is a battery charge controller. Interestingly, with the nickel iron batteries, we're going to do a presentation. I believe it's the next one in series next week, where we talk about nickel iron batteries. They are a fantastic, amazing, much better than any other kind of battery, in my opinion, for stationary use. They're fantastic batteries, and they can tolerate much wider voltage swings than most batteries. So in fact, if you have a nickel iron set and you have a moderately sized photovoltaic panel, nickel iron battery set, you can skip the charge controller. That is an option. Most modern expensive pumps, like if you go to Grundfos or Lorentz or Sun Pumps and get a good quality submersible pump, DC pump to go in your well, it has a built-in MPPT controller. That controller basically takes the DC electricity coming down the wire and sets it to a voltage that is ideal for the motor. So expensive, good equipment already has this stuff built in. You need to, with any of these charge controllers or voltage regulators, you need to pay attention to the amperage on the output side. So for instance, if we had a 300 watt, 30 volt PV panel that would have about a 10 amp output at 30 volts, but if you're going to drop that down to 12 volts, let's say you've got a 12 volt battery set, you're going to be pushing 25 amps coming out the output side of that. So you need a charge controller rated to a minimum of 25 amps. This one you're looking at here is a 30 amp, forget what they call it. It's their smaller version of the Midnight Solar controller. So whenever you're moving voltage up or down with any kind of controller, your controller needs to be big enough to handle the output, the lower voltage, the amperage that occurs at the lower voltage, because that's where the amperage is going to be higher. Something we have started using more and more at Living Energy Farm are simple little DC-DC converters. Now this little guy is different than an MPPT controller. That controller costs $350. This costs 30 bucks. You can get them on eBay. You can get them at electronics suppliers. Brand names are always better. You can also get Chinese no-name stuff if you want to. This is not a battery charge controller, so don't use it as a battery charge controller. But if you want to do daylight drive motors or daylight drive charging, we use our DC voltage regulators. We have 30 volt, 35 volt input on the PV panel coming, hits this little voltage regulator, drops it down to 12 volts, and then we can use that with a bunch of cigarette car chargers for laptops, cell phones, whatever we want to do. And again, you've got to watch the amperage on the output side, make sure your equipment is set up to handle that. As we've been using these, so far they're cheap, effective, and they're great. A more recent discovery are switching power supplies. Now with those voltage regulators I just showed you, they tend to be set up in standard voltages, which are 12, 24. You might find one at 48. The industrial DC voltages, we'll hit this in a minute, 12, 24, 48, 90, 180. You can have some voltage change, but you want to be near near the sort of design voltage. Switching power supplies, they use these with like commercial LED lighting systems. I don't know where they install commercial LED lighting systems. Maybe discos or something. I mean, discos, that's an old word. Anyway, the advantage of the switching power supply is you can take really high voltage. This particular one, I think, is rated like 120 to 360 or something like that on the input side, and then puts out a very steady 24 volt on the output side. We've got this one tied to our Sundancer refrigerator. Sundancer is a company, they make DC refrigerators. They make one, the DDR165, that's made to be a daylight drive refrigerator, and it will tolerate anything from 10 to 45 volts. It's about a third the size of a full-size household refrigerator. We'll see that again. This little thing has worked out great for us. We can run our fridge even when it's raining. Now there's a little bit of a start current on that motor, so we'll pick, we leave the fridge unplugged, so in the morning I'll look, okay, where are we using the most electricity? I'll plug it in on a high voltage system or a low voltage system. If I plug it into the high voltage system, I'll run it through this little switching power supply. And then if it starts raining after that, it's fine. The fridge will keep running. Our bigger solar rack, that 6-panel rack, is 1,400 watts. The fridge only needs about 40 watts. So even in pretty heavy clouds, the fridge will keep running. Our main loads on our high voltage system, in the wintertime, we run our heating blowers, which I'll talk about in a minute. In the summertime, we run the well more because we do some irrigation and whatnot. So we can switch. The DC microgrid that we have is very multilinear. We have a bunch of power supplies connected to a bunch of demands. It's radically more resilient than a normal off-grid design. Our systems basically never shut down. The lights never go out unless we turn them off. And normal off-grid systems fail. In fact, just a few weeks ago, we had a big windstorm and our neighbors lost power for a few days, and we were happy. We had no loss of power. And if these DC systems do start to fail, they tend to weaken. So our lights might start to dim if we overstretch the batteries. Our water supply, the pressure might start to drop. Everything kind of gives us a warning. So that's another advantage, a big advantage of these DC systems, is they're not start-stop system. It's a multilinear system that can basically never fail because it's a bunch of different systems, and you can have some issues in a particular system, but the whole system is not going to fail. So basically what happens with a DC microgrid is you figure out ways to swap out DC motors for AC motors. The easiest way to do that is to find belt-driven equipment. A lot of, like if you go to whatever department store these days and you buy a blender, that's not going to be belt-driven. It's these days they often either have the motor, like with blenders, the motor shaft that goes up to run the blender is actually the same shaft that's the central shaft in the motor. There's no coupling whatsoever. A lot of like shop equipment these days, like compressors or pumps, the compressor or the pump itself is bolted directly onto the head of the motor. So there's no belt there at all. There's just the same shaft runs out and runs the compressor of the motor. You can theoretically convert that kind of equipment to a DC system, but it's much, much easier to find older equipment. A lot of older equipment is belt driven. This thing you're looking at, you can see it's kind of dusty. I just snapped a picture out in our shop. This is a little bench grinder that I use quite a bit. We've got two bench grinders, a big one and a small one. This one's a belt drive. The belt actually comes right off the end there. With the belt, you just stick the motor in and you're good. You don't have to worry about the coupling between your device and the motor itself is much simpler, much easier. Again, the DC voltages are 12, 24, 48, 90, 180. You need to plan around those voltages. So our high voltage system is 180. You could just as easily plan around 90. We also run our lighting system and our charge system for our house. We charge the cell phones, laptops, all the electronic toys, DVD player, whatever people want to bring at a nominal 12 volts, and then we run some irrigation pumps at 24 volts. You could just as easily run things at these other voltages, but you just have to think about, okay, how are you going to set it up? How are you going to plan for it? So we can tolerate huge voltage swings, but if you're going to set up like a 90 volt system, you could use 3 panels instead of 6. that's fine, but you would want to buy 90-volt motors and not go out and buy 180-volt motors. You want to aim for your target voltage, even though these motors tolerate huge voltage swings. Let's see, about DC motors. There are two, generally speaking, kinds of motors on the market. The cheaper motors are all brush motors. Now, this is an industrial brush motor here. It's the cheapest of the cheap of Chinese manufactured motors. This one is a Worldwide Electric, that's the brand name. Leeson is an American company that makes somewhat more expensive, but still not crazy expensive brush motors. We've been okay with the cheap motors. A little more expensive motor is probably going to be better. Brush motors have replaceable brushes. You can see the little black thing on the side of the motor down there. Under constant use, these brushes need to be replaced every 2 to 4 years, depending on how hard that constant use is. The brushes themselves are pretty cheap, really cheap, in fact, but you do need to keep a stock of extra brushes, and every couple of years you need to pop out those little black plugs and stick in a new set of brushes. They're called brushes. They're not literally brushes. They're little carbon blocks usually. And there's some variability in the quality of brushes. You can get slightly more expensive brushes that are more durable, cheaper brushes that wear out faster. The other kind of DC motors that's available these days are called brushless motors. Brushless motors don't have brushes. A well-made brushless motor will run for many years with no maintenance whatsoever. The design of brushless motors is inconsistent. So how they behave, what kind of maintenance they need in the long term, it's really quite variable. Like the cheap little scooter motors we have bought, we've realized that some of those work okay as daylight drive motors. Some of them don't. Some of them need to have external electronic devices connected to them to make them work properly. Cheap brush motors, you can get little tiny brush motors that come on blowers, like you get a little cooling fan that goes in the back of an old-fashioned desktop computer or something like that. Those things are really crappy. Or if you go to an industrial supply, you get little squirrel cage fans, like heater motors, like a blower fan for an old car might have a DC brush motor in it. Those smaller brush motors, in my experience, destroy themselves. They're crappy motors. You don't want those. You either want brushless or industrial brush motors, in my experience. You don't want cheap brush motors. Anyway, a little bit about electric motor labeling. Now, these labels are not entirely consistent, and they're certainly different from AC to DC motors. But let's say you go and you buy a drill press or a heating blower for your house, and it's got an AC motor on it. You can look at the label on the AC motor, and you can swap out a DC motor that comes very close. Horsepower is one criteria. You don't have to have exactly the same horsepower. If you got a blower with a 1/3 horse and you happen to have a 1/2 horse DC motor, that's fine. But you wouldn't want to take a blower that was designed for a 1 horse motor and stick a 1/3 horse on there. You want to be kind of close. RPM, that stands for revolutions per minute. That's the speed of the motor. Those are standardized at 1800 or 3600. That's true for gasoline motors as well these days. The old standard is 1800. Most of them run 3600 these days. FR is the frame. That was the National Electrical Manufacturers Association. That's abbreviated NEMA. The NEMA frame system tells you the bolt placement and the shaft size of the motor. The really common NEMA frames for like blowers and just standard equipment, there's like a 48 frame, a 56 frame, a 56C. But let's say you get a piece of equipment, you look at it, it's got a 48 frame motor on it. If you go out and buy a DC motor with a 48 frame motor, it's going to have the same bolt pattern, the same shaft size, and the same shaft length. In other words, the relationship from where the motor bolts to where the pulley runs, the distance between those two locations and the geometry of the motor is the same, except the DC motors are often longer. Now, the length of the motor will extend away from the pulley side of the motor. So as long as there's not something getting in the way of the motor itself, you can swap out any 48 frame motor for any other 48 frame motor or 56 frame, whatever that FR number says. Now, the DC motors have what they call A-arm. On AC motors, that's generally labeled FLA, which stands, it's amperature on the armage. On the DC motor, it's full load amperage. On the AC motors, just tells you how many amps you need. V-arm, that's just usually voltage on an AC motor, tells you the voltage you need. Again, you're aiming for, the ballpark, the same ballpark of what you can produce out of your solar system or whatever. Enclosure, that's tells you what kind of motor it is, whether it can stand to be out in the rain or whatever. There's a lot of different kinds of enclosures. Duty, for any motor that you're going to run a lot, you want CONT, continuous. Like a starter motor on your car is not a continuous motor. That is a brush motor that is made to start your car, and usually the engine starts really quickly. It's not made to sit there and spin for hours and hours and hours. So some brush motors are not continuous duty. And you can see on this label, this is a continuous duty, so it can run all day, every day, and it's just fine. Interestingly, with brush motors, you can reverse the polarity, reverse the rotation with just reversing the polarity, so you don't have to worry about which way it spins. You can make it spin either way. That's not a problem. So design principles. Like I said, you cannot just take DC motors and just, or renewable energy in general, and just stick it into the existing economy or the existing way we do things. You need to think about what you're doing and how you're doing it. Your goal is to provide services. And you know, if you want drinking water and you want water to take a shower, the goal is to pump water, not to provide an electrical support system for an existing AC pump. If someone tells you, I want to power my clothes dryer with renewable energy, tell them they need to get a clothesline. If they want to power their vacuum cleaner, buy them a broom. You really need to think about how you're organizing things and how you're using energy. Because if you start trying to hit these heavy energy demands and these existing lifestyle patterns with renewable energy, well, that's what all the environmental groups are telling people these days. It's a big fat lie. It's really excruciatingly frustrating for me because it's wreaking enormous environmental havoc. Just a couple of miles away from Living Energy Farm, they just bulldozed 250 acres of beautiful hardwood forest. They piled the trees up in the stumps. They burned them. The carbon release from that whole project is massive. We have a big creek, a small river that runs across the back of our property. Of course, they do the erosion control that they're supposed to do. It's completely inadequate. They completely silted up our creek, all of that to put up 30,000 photovoltaic panels. So middle-class Americans can feel good about sitting in their hot tub using electricity. Anyway, forgive the rant there, but adding renewable electricity to the existing systems is stupid, environmentally destructive. It's a horrible process. It's no better than coal mining. So now we have solar strip mining where we bulldoze forest and put up PV panels. So if you're throwing all that out the window and you're thinking, okay, so I'm not going to do solar strip mining. I want to use organize our lifestyle. We're going to organize our energy self-sufficient communities. How do we design that to make it work? Number one is you're going to store energy as low-grade heat or store energy in forms other than electricity. We store heat to heat our buildings in the floor. We just pump the heat under the floor through rock and dirt, heats the building up. You're not trying to store electricity. Number two, we're refrigeration systems. We're storing the sun dancers, or you could build a refrigerator like that on your own. Instead of having 2 inches of insulation, it has 6 inches of insulation. Again, you're not trying to store electricity. You're trying to store, you could say storing coolness. It's really storing the absence of heat. But in any case, you're storing that instead of electricity. For water, we don't try to run a water pump at night. We have slightly larger water storage tanks. So we're storing energy as pressurized water. We're not trying to store electricity. Hot water for showers, again, we're storing it in, we have big solar storage tanks. There's where shared use really matters, because to build a good solar storage system in a temperate climate for 2 people will cost you $3,000. For 12 people, it'll cost you $4,000. The return per person drops dramatically as you go up in the number of people using your hot water system. So with our daylight drive, we're doing all of our electronics, we're charging during the day. We swap them onto the batteries some, but again, we have the capability. We're basically using the lithium batteries that are in cell phones, smartphones, all of that, and we're keeping that system separate from the central batteries that light up our lights. We have a nickel iron set that lights up our lights, but the conventional off-grid design, you have one battery bank that carries everything, so when that battery bank weakens, the lights go out, you can't run your computer, you can't do anything, you can't take a hot shower because your pump went out. Crazy design. For our system, we've already stored the heat in the building, the refrigerator is cold, the pressurized water is stored, the hot water is stored, so if the battery goes out on my cell phone, the only thing it affects is my cell phone, nothing else. So a DC grid is a multilinear system. All of these systems are self-supporting. We can swap power between the different systems if it suits us. but the system's weakened, they don't fail. This is your basic sort of design principles of how the system is put together. Now, we looked at this picture before of this is the overhead satellite view of Living Energy Farm. Now, this was taken probably a year ago, whenever Google Maps or whoever the heck takes their pictures. We have built a shop. The main house is the big black roof. This kitchen is a smaller black roof. There's a barn right next to it where we do our seed processing. There's a shop right behind the kitchen that doesn't show up on this picture. And our biggest solar rack is back, and the well is down the hill. That's the reason that solar rack is back behind the houses like that. We have one PV panel right on the roof of the barn that feeds power into the kitchen, another PV panel that independently feeds power into the kitchen. Our main solar electric control center is right there in the kitchen. And then our shop, which is behind the kitchen, is where all the high voltage stuff runs. So the idea is to show you basically that this is a village level integrated system where everything is kind of close to everything else, basically. And this is a multi-family shared house. We have 2 families there now, and we bring in interns and whatnot as it suits. But this is all closely tied together. You're not trying to take DC power and push it 2 miles away. It's all within a few hundred feet. And the low voltage DC stuff is all pretty close together. We're not pushing low voltage DC all that far, although we are actually pushing the 12 volt stuff probably a little further than we should, maybe 100 feet. But it's for DC LEDs that are very, very small. So the actual amount of current we're drawing over that distance is very small. So this is our high voltage rack. That's the 6 panels that runs. Again, there's a long list, and the list has actually gotten longer since I drafted this. I just cut this out of another document that I'd used before. Its most important thing is our main well. It also runs the heating blowers for the main house, the heating blowers for the kitchen. The heating blower in the kitchen doubles as a food dryer. We have some seed drying equipment. We run high voltage. Big firewood saw. This is a buck saw. I think we have a picture of it coming up here shortly. In the shop, I have drill compressors, 2 grinders. We have band saws. We're bringing in a lathe. We have other seed processing equipment, seed cleaning equipment. The amazing thing about this high voltage DC, so that's 180 volt system, 1400 watts gives you about 1.5 horsepower, but we can actually run 2 horsepower, 3 horsepower. The motors speed up, slow down. We can run motors on a cloudy day. And there's no electronics, there's no computers, there's not a single integrated circuit anywhere between these PV panels. Now, each one of these PV panels has a diode in it. That's a very simple little electronic device that the manufacturer put in there just to make sure the panels don't draw electricity back out of your batteries at night. And then there's the DC brush motors. The DC brush motors, that technology hasn't changed since the 1800s. So there's not a single transistor, resistor, diode, well, the diodes I mentioned, and no integrated circuits, no electronics whatsoever, which makes it a very simple, very durable, very flexible system. Sun comes up, motors run, sun goes down, motors quit. Super simple, doesn't go wrong for the most part. I will warn you what we have learned about DC electricity. We do run these motors in cloudy weather, but particularly if the voltage starts to drop in cloudy weather, that DC current beats up switches pretty bad. So the current, the amperage coming off of this solar rack is about 8 amps. So you would think a 10 amp switch would be fine. Well, that DC power will destroy 10 amp switches. It will destroy 20 amp switches. We are using 30 amp switches currently. I believe coming up, yep, this is the next picture. So this is the boxes that are on the side of that solar rack that you're looking at. This is the framing of the solar rack for those 6 panels. These are $50, $60, 30 amp switches. That happens to be an old switch. The one on the left that I just had laying around in some spare equipment. Now these are outdoor switches. If you're using outdoor stuff, you want outdoor, switches that are made to get wet, basically. They can stand being in the rain. So for our main central switches, I'm using big, heavy switches. That's an expense, but that DC power, you start throwing these switches in cloudy weather, you'll hear an arc. It's like an arc welder going off, and a normal switch just gets melted. Now we do have, this is a smaller normal switch here. We're just a little more careful about where we switch it. And I'm not putting a $50 switch next to every motor. We have cheaper, smaller switches next to the motors, and occasionally we burn out one of those switches and have to replace it. But you notice how all of this stuff is in conduit. We wire this as if it were AC equipment. It's code specified AC style wiring. And if you know how to do that kind of wiring, great. If you don't, find somebody who does. It's all grounded. It's all set up as if, this can handle 600 volt AC power by code. It's handling 180 volt DC. Like I said, it can hurt you. It can start fires. Don't mess with this if you don't know what you're doing. But this is how it works. That switch is the one that goes to the main house. This is the switch that goes to the pump. We throw that switch. We're running the pump all day long. That's a timer that goes to the pump when we just want to pressure up the system and we want the timer to turn itself back off. And that's the switch that goes to the shop that runs all our shop tools. For the water system, we were on a Grundfos pump. Here's a friend of mine holding the pump. You've got two kinds of pumps. The Grundfos and Lorentz are the big, they're both German companies. Some pumps is pretty similar. Grundfos and Lorentz are both making what they call a helical rotor pump. If you're looking for a pump that's going to give you residential style water pressure, even in cloudy weather, you're probably better off with the helical rotor. We do a bunch of irrigation, so we actually have what's called a centrifugal pump. The centrifugal pumps are high volume pumps. You'll notice the funny thing about that helical rotor pump is it's only about 2 inches around. It's a tiny little narrow pump. This is a Grundfos helical rotor. They made that to drop in wells in the non-industrial world where they've got a lot of 2 and 3 inch wells because they're drilling these wells by hand or with really small scale equipment. So that helical rotor pump is made to go in a really small well. It will give you full pressure output with a tiny little bit of electricity, but it's not going to have quite the volume performance of a centrifugal pump. And they have the same warranty, at least Grundfos does, on the helical rotor that they have on the centrifugal pump. But I personally believe that the centrifugal pump will probably have a longer lifespan. You could put the centrifugal pump or helical rotor pump on a pressure switch and run it just like an AC pump, but in cloudy weather, that pump would run a lot because it would take it a long time to bring up pressure. We run it on a timer so the pump doesn't run as hard. I think we'll get 20 years out of our pump that way. We're trading off a little bit of manual controls for extending our pump life. At least I think that's what we're doing. Most residential homes in rural areas might have a 20-gallon or 30-gallon storage tank. That's a 120-gallon tank. We have 3 of those if you include the house and the kitchen. We found a good source for fiber wound tanks. You'll notice that's a gray tank. On the East Coast, all the well water is acidic. There's nothing wrong with it. It just happens to be that there's no limestone in the ground, so that the fiber wound tanks are better. They don't put rust in the water. So we just have bigger storage tanks. They're not free, but it's much cheaper than the way it's normally done with normal off-grid design. So we tweak the timer, that pump turns on, pressurizes the tank, and I can take a shower at midnight with solar hot water that was stored from 2 days ago. You've seen this picture before. If you've seen our presentations before, this is the outside of our house. That huge glass thing up the middle is homemade cheap solar hot air collectors. Again, there's a word of caution here. A well-made, and these are probably not well-made by that criteria, a well-made solar collector in a dry climate can reach ignition temperature. You don't want a wooden frame around your solar collectors. This is what happened back in the, I'm not sure when exactly, 70s or 80s, somewhere back there. A company in California made redwood framed solar hot water collectors and realized some years later that under particular conditions, dry conditions, when there's no fluid being pumped through the collectors, that they could actually set themselves on fire. So we have metal framing all around that. We use steel studs to bump up the glass so it's not sitting right on the wooden trusses. Some ventilation behind it. Here, again, proceed at your own risk. If you don't know what you're doing, figure this out. But there is some small risk there of fire. Now, this is the industrial blower that's pulling the heat off the roof. There's a ductwork system that takes the heat under the floor. Showing you a picture of it. This is a 3/4 horsepower blower. This is a big blower. It's about, if you have a normal air conditioning heating system in your house with forced air, this blower is about twice as big as what you have. Now we have, this is on the hot side, which makes it an expensive blower. The motors, most cold side blowers, the motor's actually in there with the blower, so the air streaming through the blower cools off the motor. We're pulling, I wanted to keep a negative pressure on these panels on the roof because I know they're leaky, you know, they're homemade. So we put it on the hot side, which makes for a more expensive blower. I picked this one up on eBay for, it'd be a $1,500 blower new. I got it for a few $100, which was nice. But it's big industrial stuff. The DC power has got as much moxie. In fact, it has more kick than the AC power does. So you can run industrial equipment. That works fine. This is a layout of just how that heating system works. So the hot air collectors, that big glass stuff you were looking at, is represented by this part of the drawing up here on the left upper drawing there, where there's a red arrow. Collects the heat up there. That blower pulls it down a ductwork system, forces it under the floor. goes through a bunch of rock where it stores the heat back up and back up to the roof. This is another drawing of the same thing. You do reverse return. Anytime you're trying to pump air or water through multiple tanks or under a floor, you shove it in one corner and pull it out the other corner. So the air travels down a ductwork system. There's slots in the duct, goes under the floor, heats up the house. Again, we're storing energy in some form other than electricity. For our DC daylight drive equipment, we do a bunch of different things. This is my buddy Eddie. This is our firewood saw. Now that is a big old buck saw. That blade is about 32 inches across. It's made to run off of an old school flat belt tractor, so a 30 or 40 horse engine. A little gray thing up there to the left is a 1.5 horse DC motor. Now when we want to run this saw, we actually do go ahead and turn off the blowers and the other stuff so we can focus the power, and we'll do this on a sunny day. So the way this saw works is the blade stays still and the table moves. You can throw a 6-inch log up there. We are still, we bought the land where Living Energy Farm is 8 years ago. It was cut a year or so before we bought the land. We would never clear cut it, but somebody else did. We're still living off the tree limbs from the cedar trees that they ran over 8-9 years ago. That saw will bite through a 6-8 inch chunk of wood as fast as a chainsaw. You roll the table back. By the time you've moved the wood over, the saw has come back up to speed. So that little 1.5 horse motor's got a lot of moxie. Now the interesting thing in thinking about horsepower is that the electrical horsepower, one electrical horsepower is worth 2 or 3 gasoline horsepower, and that's because an electrical motor has torque in full rotation. So you can, to some degree, undersize electric motors when you're swapping out for gasoline motors. Now in this case, the motor is pretty undersized. This saw, if it was hooked up to a 30 horse diesel engine, could whack through a 12-inch log without thinking about it. We just stick to small stuff. I don't want to split 12-inch wood anyway, so we stick to 6, maybe 8-inch stuff, and that's fine. That's more than enough firewood. We spend maybe 1 day a year processing firewood. It's not a lot. Because we've made our system so efficient, we don't need a lot of firewood. This is Rosa. Her full name is Rosianka. She's named after persimmons. We'll talk about that in the presentation where we talk about orchard planting and fruit tree production. That's another part of Living Energy Farm. You can see her hair is swept back. That's a tiny little 1/3 horse motor. So that's, what is that? Yeah, 1/6 as much horsepower is what's running that big saw. And it still sounds like a freaking airplane when you turn it on. This is one of the blowers we use for processing seeds, winnowing seeds and whatnot. So you can sit in front of that airplane blower if you want to in the summertime, keep yourself cool. More daylight drive equipment. The red thing in the upper left there, that is a grain grinder. We run that a lot. We grind all of our own grain. We grow all of our own corn. We feed the corn, use the corn to feed ourselves. Nixtamalization is the term for the American Indians. They used to mix wood ash with corn. That's how you make corn tortillas. It makes the corn kind of sticky. We just learned how to do that fairly recently. We grew some wheat last year. We have a wheat crop this year that I think is going to be big enough to feed ourselves for the whole year. We don't keep a lot of animals, and we'll talk about that, why we don't keep a lot of animals in a different presentation. But we do have a small flock of ducks. We feed them with the corn and the wheat that we grow. So we don't buy any flour, no flour of any kind. We grind it all ourselves. This is a picture of some of the equipment in our shop. That is an old school, really large drill press. The big drill press like that, it's a big heavy thing, gives you the option of drilling bigger, heavier chunks of metal. In the lower left, there's a compressor. Now, again, I was talking about when you start thinking about swapping out these DC motors, that is a long motor. So the motor that was on there was a 56 frame motor. This is a 56 frame DC motor. So it bolts up to the same bolt pattern on the compressor, but the motor does stick out the side of the compressor. And this is an old Sears compressor that's belt driven. Again, if you go out and buy just a brand new compressor, you're going to get a direct coupled compressor, and it's going to be a little bit more annoying to figure out how to connect it to the motor. Find an older one with a belt, you just put a belt and a pulley on there and you're good to go. Let's go on to the next page here. This is our solar lighting system. One individual PV panel, that particular panel happens to be about 250 watts. It's actually much bigger than it needs to be. There's the charge controller, you've seen that before. This is a whole separate system. So this is part of the DC microgrid as we call it, but it's totally separate from the daylight drive system that we just went through. We got the little charge controller feeding the nickel iron batteries. I'm not going to talk a whole lot about those because we're going to do a whole separate presentation on them. I will say that the nickel iron batteries in our whole multifamily setup, we actually run some power tools tool off the nickel irons as well, but mostly we just run lighting. The lights never go out. That is a 100 amp hour set. We had a 600 amp hour set of lead acid batteries when we first started out, and we only had the kitchen. It was before we built the house, and the lights, we couldn't keep the lights on. The lights were going out. Pretty frustrating. That is an 18-volt cordless power tool. You can't see it in this picture, but that cord actually runs all the way back to those nickel iron batteries, and we can run them at 12 volts. We can run them at 24 volts. The miracle of DC motors is they run, again, with all these fluctuating voltages. That's the bigger bench grinder you can see in the background there. This is another high voltage tool. That drill is actually out in the shop. So here's yet another separate electrical system. This is yet another. This is the last of the PV panels. That PV panel goes to the little voltage regulator that goes to a whole line of cigarette lighter plugs. Since I took that picture, we've added some more cigarette lighter plugs. And people just line up with, we can charge 2 or 3 laptops and cell phones and get a whole bunch of stuff plugged up all at once. And there's no such thing as overloading it. Who cares if you overload it? That stuff just charges a little bit slower. So these days, I guess internet's the new television. I sit up late at night. I'm trying to find a lathe for our shop. So I've been cruising Craigslist and eBay, and I'll stay up half the night if I want to. I can sit up and watch a movie. It doesn't matter. We got plenty of power. And this is with a couple of families and a bunch of interns hanging around. We still have plenty of power because we're using this power very, very efficiently. We're not trying to run on some big lead acid battery bank. It's just fantastic how well these systems have worked. And that's part of the reason I've started talking about it more. It's like, wow, this is like light years better than normal off-grid design. And you can watch a movie all night. The building stays warm. Take a hot shower anytime you want. Drink a cold beer. I don't drink beer. We can do anything you can do with a normal system, except you need to put your clothes on a clothesline instead of running a dryer. But in terms of basic comforts, we can do anything, and it's dramatically simpler, cheaper, more durable systems. Anyway, I'm very enthusiastic about how these systems work. Very effective. Great systems. This is our solar Sundancer refrigerator. As I mentioned, we have 2 different modes of how we run this refrigerator. That is a PV panel. So on a day when it's sunny, and if I look and say, wow, Deb is my wife. If Deb's running the irrigation system today, okay, well, the high voltage system's loaded up a bit. I'll plug the Sundancer straight into the PV panel. Oh, well, actually, it's a cloudy day. We're not running the heating blowers. We're not running the irrigation. I'll run it through the little, the switching power supply. So basically, every morning, I just plug that refrigerator into one or the other. So there is some maintenance or some daily decisions that are made about how we run power. But that said, there we have our little refrigerator. That thing will run as a chest freezer if you want to. It stays plenty cold. And no coal, no nuclear, no frack gas. And we get to have cold lemonade, cold beer, cold whatever you want. Stick your leftovers in there. And we are not supporting the big evil corporations. We're not contributing to global warming, at least not as much so if you're using all those nasty power sources. If you live in a warm climate, in the tropics or Southern California, you can use a very simple hot water system. Take an old chest freezer or refrigerator, take a water heater that still has a sound tank, strip the jacket off the water heater, paint it black, put it in the chest freezer, put a piece of glass, or if you don't want to be that fancy, put plastic, double pane patio glass is ideal. Tilt that thing up so it's out in the sunshine, and that's called a batch collector. You heat up the water in the tank, you just hook up your pressurized water to that tank, the pressure pushes it through, it works fantastic. In a temperate climate like we have in Virginia, a batch collector like that's good for maybe 7 months out of the year, and what you need for year-round hot water is what's called a flat plate system. This is not specific to LEF, this is over-the-counter equipment. Those are 3 flat plate collectors. We have a total of 8 flat plate collectors on the property, 6 for the main house, 2 for the kitchen. It's again a daylight drive system, so that's a tiny little 20-watt PV panel. That little pump is called an LCID. The company that makes those, it's just a guy in Florida that makes them. It is a fantastic technology, though. That tank is made by a company in Florida, also in Florida, called AET, Alternative Energy Technologies, I think it is. It's a nice stainless tank, not cheap, but very durable. This system, I'll tell you, the standard design is to run these systems. It's a closed loop, so you're pushing antifreeze up into those panels. It runs 12 months out of the year, no problem. The normal system design is to put a 30-pound pressure release and run it at 12 to 15 pounds pressure. On the closed loop side, your antifreeze side, I'll tell you, if you have experience with these systems, get rid of that 30-pound pressure release, put a 50-pound pressure release, push your operating pressure up to 30 pounds, and it will run for decades with no problem. With the lower pressure, they crap out after a while sometimes. I'm talking fast here because we're going to run out of time before I run out of get done with the presentation. But in any case, this is the main electrical control center in our kitchen. This is where all of our electrical systems come together. So the box down there has got the nickel iron batteries in it. There's PV panels outside, the low voltage PV panels. One of those PV panels feeds the midnight solar charge controller that takes care of the batteries. That's all of our lighting. We have the little voltage regulator here that feeds the cigarette lighters, plugs where we do all of our charging for all of our laptops, smartphones, all of that crap. We have a plug here where we can run power tools off the nickel iron batteries. Out in the shop, I have more low voltage plugs. We have the high voltage plug here. This runs the heating blowers. We can also just plug other equipment, like we've got a washing machine now that runs on high voltage. I can plug that into this plug. And we can also switch back and forth across these different systems. So there's a plug, a cigarette lighter that's plugged back into the nickel iron batteries. So if I forget, heaven forbid, I forget to charge my laptop, at 10 o'clock at night, I have something important to do, just tie the laptop back into the nickel irons. I swear to you, with these nickel irons, you can try to discharge them and you almost can't do it. They resist discharge in a way that is miraculous. There's no other word for it. I'm amazed with these batteries. And then like with the fridge, as I said, we've added some more equipment since I took this picture. I've got a plug right there and I just swap. When it's cloudy, I plug the fridge in there. When it's sunny, I plug the fridge in there, just depending on what's going on. Another interesting detail, that little gizmo right there, a shiny thing right below the yellow cord, that is a surge arrestor, particularly if you live in an area where you have thunderstorms. Another advantage of this whole multilinear system is if we take a surge on a lightning strike, if you take a full-blown lightning strike, God help you, but in thunderstorms, there are a lot of surges that can go through electrical systems. Because these systems are all separate, we won't lose all of our equipment. We might lose a charge controller, we might lose a voltage regulator. The one strike that we took early on, we actually lost 3 light bulbs. That was the extent of our damage. But if I had all of this system tied together, which is the normal off-grid design, and we took a heavy surge, it would blow right through your surge protector. It would destroy the well pump and the charge controller, destroy everything. So it's another advantage of the multilinear system is that these, so that they were protected to a certain degree at least. That said, you are better off with putting some surge protectors, particularly on your more expensive equipment. Now, I couldn't help. I drafted this thing a couple days ago, and I thought it was a dark, cloudy day, and I just spun around in my chair. I said, let me take a picture of what we're doing on a cloudy day. This is like the worst of the worst, bad weather. There are 2 laptops charging, 2 cell phones. There's our internet device. That's a hotspot. There's the high voltage switching power supply. You notice the fridge is plugged into the high voltage right now. So all of this equipment's running. You can see the little lights on. All of this equipment's charging, even when it's cloudy, even when we don't have that much power, and it's all floating. In other words, none of it's going to shut off because the voltage is too high or too low. It all just kind of goes with the weather. It's all very laid-back equipment. So this is an actual, from a couple days ago, cloudy day, a worst of the worst case scenario of how these systems work. So your laptop is going to charge a little bit slower on a cloudy day. Okay, big deal. None of this stuff shuts down. It keeps working. It's really quite fantastic. We put this in our newsletter recently because as much as I tell people you really need to do this at a community level, and people keep asking me, oh, can I do a little bit? Can I bite off a piece of it? It's like, okay, you can bite off a piece of it. But I'll tell you my experience with solar hot water, for instance. Solar hot water actually has a much better payback than solar electricity, than photovoltaic panels. You wouldn't know that because of the idiotic politics we have now where we're bulldozing hardwood forests to put up PV panels. That is insane. But because rich people want to, quote, do something, forgive me if I rant, but it really upsets me to see people bulldozing hardwood forests to put up PV panels. But it really comes back to the fact that we're privileged and we don't want to change our lifestyle, so we're going to add something onto that lifestyle. So we add on a couple of PV panels, and then a lot of people start doing that, and then that gets legislative support, so we think PV actually has a good economic return. PV added onto industrial systems has a horrible return. It has no return at all. Hot water has a better return, But here's what happens with hot water systems. I've built a bunch of them. People have their electric heater or their gas heater, and they say, put on a solar system, and we'll feed the solar hot water into my gas heater. So when I've got good solar hot water, I'll take a solar hot water shower, but even if it's been cloudy and cold, I will still have solar hot water. Well, what happens is the solar system fails over time, and then they don't even notice. The power bill goes up a little bit. So these systems don't get along all that well. You can't put renewable energy systems in the same bucket with how people are accustomed to using fossil fuel systems and expect them to work. But all of that said, that was a preamble to, okay, you want a solar charging system, PV panel, and a $30 charge controller, total cost maybe 150 bucks. I'm not going to go down this whole list. Download this thing, read it yourself. This is biting off this DC system a piece at a time. This is a uranium mine. If you're doing grid-tie solar, you're still using nuclear power. The grid out there, the AC grid, is roughly in thirds, basically. It's about a third coal, a third nuclear, a third gas. And what's happening is the coal side of it is shrinking and the gas side is increasing because of frack gas. If you haven't seen Gaslands, it's a great movie. About half the gas that they frack just goes right up into the atmosphere because it comes through the ground all around the frack gas wells, and which has a horrible impact on climate change. But when people want to add the grid-tie solar, it's so they can run their tumble dryer. They don't have to change their lifestyle. Well, look at this thing. We're destroying the planet for your tumble dryer. Is your tumble dryer worth that? This is mountaintop removal. Some of these mountaintop removal sites are as big as New York City. They're massive. But because they're out in Western Virginia, West Virginia, Tennessee, Kentucky, these areas where there's not a lot of people, they can do these massive strip mines. They stopped calling them strip mines and started calling it mountaintop removal. Is a vacuum cleaner worth this? It's like, okay, you can't run a vacuum cleaner at Living Energy Farm. We don't have an AC plug. We don't have any vacuum cleaners. We have floors that we sweep. Is your vacuum cleaner worth blowing up an entire mountain range? I can drink a cold beer. I can surf the net. I can take a hot shower. My house stays warm in the summer. We have air conditioning, warm in the winter, cool in the summer. We have air conditioning. We haven't actually finished building it yet. We pump the irrigation water through the house. We can have all of that and not the tumble dryer. Do you want to blow up the mountain range to keep the tumble dryer? Well, you can't do this as a reaction. You need to plan. We need to work together as communities to make this work. Those are sludge ponds, actually, those black things. And those things break down, and then these huge piles of sludge go into the rivers. The other big side of this is supporting democracy. I published a book back in 2007, 2008, Integrated Activism. And what I said was, I traveled all over the country. I hope the presentation is still out there. If it's not and you want to see it, I can get it to you. Get in contact with us. I call it the Constructive Panic Road Tour. And what I said was that because of the energy constraints, okay, they're going to frack gas, they're going to do all of that stuff, but the industrial economy can't grow forever. It puts more pressure on the working class. That polarizes our politics. Lo and behold, 4 years later, we get Donald Trump, and our politics are getting even stupider. That's predictable. I mean, you can go back and look at how the politics evolved. You can find every speech that's been made by our nutcase politicians. That speech was made back in Roman times. Our politics are very connected to our energy supply. It's very connected to, these things are not separate issues. And I said back then, I will say it now, sustainable communities are an alternative to economic centralization, an alternative to corporate rule. This is the solution. Sustainable communities are the solution to not only our ecological crisis, but our political crisis as well. I said it back then, I'll say it again, and not only are sustainable communities an ecological solution, they're the only viable solution to climate change. We're running out of time here. This is Shanghai with 2 feet of sea level rise. The actual sea level rise that our children are going to deal with is 230 to 260 feet. That's when the polar ice caps actually melt, the Greenland ice sheet melts. Climate change is 5 times as fast at the ice caps as it is at the equator. So climate change really means we melt the ice caps. That's what it really means. Climate scientists are being harassed these days, death threats, all of this stuff. So they try to talk in non-alarmist language. They're not going to talk about a 260-foot sea level rise, but that's what we're facing if we don't get our lifestyles, don't get this situation sorted out. But at the end of the day, oh, is that my last slide? It is my last slide. I thought I had one more. Anyway, so we got a choice. We can watch our democracy fall apart and sit around and wring our hands. If you want to protest and get out in the street and do that, that's great. I've been tear gassed, arrested. I've done a lot of environmental organizing. It's great to resist the powers that be when they're trying to mess up the planet. But if we really want to fix the problem with our democracy and fix the problem with our climate and fix the problem with unsustainability, all of those problems, the solution for all of those problems points in the same direction, and that is towards energy self-sufficient communities that are economically viable, that support the future of democracy in our society. So anyway, I talk a little fast there because we're going through a lot of material. There you have it.
Awesome. And all right, everybody, that was amazing and a lot of information in that presentation. So that was great. And by the way, you can go back and watch the replays. Last week's is still up for the free people, and for elite and pro members, you get all these videos as long as you stay member with EAT. And today we have a handout. You can get the PDF version of whatever the presentation was today is in the handout section, and you can just click and download that and save it to your computer. So if you have any other, let me see if there are any questions from the audience, and I can see a bunch of questions already. There's one from Alicia. She asks, what are your annual operating costs for the electrical system?
Our annual electric operating costs are maybe $10 worth of distilled water. It may be $20. Maybe if you count the brushes, it's almost nothing. We have to put distilled water in the nickel iron batteries, which you can make yourself. I have a little solar distiller. I just haven't gotten that completely operational. And distilled water is, whatever, it's super cheap. Put brush motors in the DC motors. Like I said, every couple of years we have to replace brushes. Those things are dirt cheap. The degradation rate on PV panels is about 1% per year. So over the next 50, 75 years, somewhere down there, somebody's going to have to replace the PV panels. The DC motors will eventually wear out. So there is some expense there. The nickel iron batteries, they will probably last. We have one nickel iron battery that's, I think it's 100 years old. Maybe it's only 60 years old. I'm going to put 40 years on our current set of nickel iron batteries at $1,000. That's a $25 per year degradation cost. So I don't know, if you added all that up, maybe you'd have $50 or $100 worth of degradation in all of these energy systems. Keep in mind that, that's compared to a monthly energy bill for an AC system that is whatever it is. Some people pay hundreds of dollars a month, or for a standard off-grid system that has $1,000 a year battery degradation cost. The degradation cost on these systems is radically cheaper than any other system.
Right. So here's has it ever happened in your farm that you run out of power, or have you thought about, like, if I have shortage of power, what should I fall back on? Is there a plan for that?
Well, you plan for a system that doesn't run out of power. We have never, well, let's say this. Okay, so it does happen occasionally that I charge my laptop up and I stay up until midnight, and oh, okay, the battery runs out on the laptop. I could go back and charge it up, but by midnight I'm tired to go to bed anyway. That's not a big issue. It did happen once that I went away for about a week from Living Energy Farm, and I left the interns in charge basically, and they left the lights on in the house for about a week. And when I got back, they looked at me and said, the lights are starting to get a little bit dim. And I said, okay, well, you left them on for the last week. And they said, oh, well, what should we do? And I said, well, we'll turn off the lights. So the power never actually goes out. The lights start to get dim. If your laptop runs out of juice, okay, well, that can happen even, that can just happen. You could go plug it back in. Because these systems are all separate systems, things don't shut down. The water pressure can run low, right? If we have, like I said, we have a centrifugal pump. If you really want to make sure you never run out of water, just get a helical rotor. Those things will pump water even with a very small amount of energy. If your systems are designed well, they never shut down. I know that sounds crazy because everybody who's used to off-grid living thinks we do not have a generator. Now, I don't try to run the drill press at night because there's no power at night. We don't wash clothes at night. We wash clothes during the day. So we do adjust our lifestyle based on the weather, but we don't do without. The systems never shut down. They speed up, they slow down, but they don't shut down. That's not a problem.
Awesome. Okay. So will your system work on areas where there is not enough sunlight or enough days of sunlight? How will that work?
Well, that's the first principle of ecological design is solutions are always local. Talked about this. We'll talk about this a lot more when we do the green buildings session. So, you know, the tire house, the underground house that works great in Arizona is a bad idea in Virginia. The house that works great in Florida is not going to work in Maine. Well, the same is true for energy. You know, we live in an area that is moderately sunny, moderately cloudy. We're not nearly as sunny as Arizona, and not nearly as cloudy as, I don't know, the Arctic Circle or maybe Seattle in the wintertime. You'd have to think about it. You'd have to simply sit down and look at what are my needs and how do I meet those needs? What are the demands? Again, we've been so trained to think about this as an energy issue. It is not an energy issue. If you approach it that way, you're really going to defeat yourself. You are not trying to generate energy. You're trying to figure out how to pump water, how to keep the house warm, how to keep the house cool, how to run your computer, whatever you need to do. And those solutions will be based on whatever resources are available. Maybe if you live in a really cloudy area, it's not as cold, and I mean, I don't know. You just have to figure out based on what's around. The other thing is that photovoltaic panels, in my experience, and there's monocrystalline, polycrystalline. There's different kinds of panels, and there's different configurations, and you could research that more. We've had no need to research it. The panels we have about 10% output, even in heavy clouds. 10% is enough to get us by for what we're doing. So you can scale the systems, you can adjust to what you need. And that said, you know, it is going to be harder in the Arctic Circle than it is in the tropics in terms of supporting, you know, if you're talking about a zero fossil fuel lifestyle. I'm not saying it's going to be, different locations are going to present different challenges and different resources. But it's not an energy issue, it's a design issue. So keep that in mind.
All right. Excuse me. I have a bunch of comments. Jeremy says, wow, amazing. Alicia says, thank you. So she got her answer. Kate says, I missed the first half. It's early in New Zealand, but looked like a really great session. We'll watch it again with my partner. Thank you. All right, thanks, Kate. You can watch. You can always go back on our website and watch the replays. Last week's is still up, and I know Kate is a pro member or an elite member, so she get all the replays as long as she is a member with us. So thanks for that comments, and everybody. I don't see any other questions, so we'll stick around for a couple of minutes, but we'll let Alexis go in a few seconds. So if you have your questions, type them in. Otherwise, we'll say goodbye and stay tuned for the webinar highlights of the week, which is coming up next. So Alexis, as we are wrapping up, if you have anything else that you want to end with, please go ahead and we'll end on that.
Well, just had a good time doing it, and we'll see you next time.
Hey, thank you everybody. Thanks for watching.